Thanks very much indeed, Chandra.
Yes.
That was a very interesting talk. I'm going to throw the floor open to anyone to ask questions of Chandra on any aspects of his talk. Joachim?
I have. Yeah, so I'm thinking about your idea about tension field as a source for drag. I think you wouldn't even be able to observe a drag if the tension field was superfluid, if it didn't have any defects in it, if it didn't have the, what's it called? You talked about that there should be some loss of energy somewhere, or what did you say?
Yes, that is the
yeah. But if you assume there is no loss of energy in the tension field, if the energy persists forever, which is energy conservation forever,
yeah.
then I think you wouldn't be able to observe a drag, even if there were a complete tension field. Think about superfluid helium, for example.
Yes, yes.
The particles in superfluid helium are, I've seen it myself because I've been teaching, what was that, solid state physics, and we had superfluid low temperature physics experiment.
Yes, and the
you can create smoke rings. You can make smoke rings. That's a knot that finds itself, and the knot dimension is arbitrary. Yeah, the knot radius is arbitrary. That if you have a small radius, it's a high-speed particle. If it should have a large radius, then it's a low-speed particle. So you can create arbitrary speed particles up to the speed of the medium, which is the sound velocity in helium-4.
That's a
superfluid helium-4.
It's a very nice, important comment, because yes, I am not into.
Yeah, and if you look at, yeah,
yes.
Let's think about you have two such particles going in two different directions.
Yes.
You would see them as two smoke rings.
Yes.
Right? But if you imagine yourself being one of those, inside one of those smoke rings, moving with the smoke ring, the only thing you can measure is how on the scale that you see, how the other smoke ring looks like. And then the only thing that matters, I think, but I haven't proven it by experiment or mathematics, is the relative velocity between those two smoke rings. Not the absolute velocity. Not at all the absolute velocity.
Well, I am more assuming, I understand your point, but I'm more assuming that CTF is the absolute rest frame, whereas the undulation.
Yeah, I don't object to that. I mean, you wouldn't be able to observe it. That's my objection to your description. There's the experiment you suggest to NASA wouldn't prove, you wouldn't see that effect. And I think it would be easier and most cost efficient to do it in a superfluid helium instead, using smoke rings.
Well, maybe we should start collaborating on that, and I'll read up on the, in fact, I like your idea for this reason. The superconductivity, the electron is moving almost without resistance, even though it is within so-called physical solid.
It is, otherwise it wouldn't be superconductivity.
Yes, that's what I'm saying. Even though I have not specialized or spent a lot of time on it, but I see your point.
But I don't talk about that because that's very difficult to see, because you think in 3 dimensions. And to see in 3 dimensions, it's much easier to see inside a thermos that are made in glass, a vacuum thermos that is made in glass, and look at superfluid helium inside there.
Yes.
Because then you can actually see it in 3 dimensions in real time. And make video recordings of it.
Write up and submit to ESA, and I will contribute whatever you want me to write.
So the same experiment, but done in helium-4, and I can try to get it done by students in Chalmers, where I worked.
Okay.
Yeah.
That sounds.
It would be interesting, but I think it would prove that it wouldn't be observable.
That's good. We need to go from all angles because, as I said, that we are all blind. And when a lot of blind people pull their ideas together, they can find out our shape of
I have a feeling that you would like to be God, being able to see the superfluid without being inside it. And you can't. You're just one of the particles inside it.
Yes.
And then you wouldn't be able to see it.
In fact, I make the comment that it puzzles me, although we are now way, the hindsight 2020, why Niels Bohr was so gung-ho on pushing that quantum mechanics is correct, complete. Whereas it is trivially obvious today that all theories are incomplete by nature. And not only that, his point that observer creates a difference. Well, again, observer designs the instrumental concept and makes the instrument, but human brain is the interpreter. My instrument is the real objective observer because it interacts with the interactants within my instrument, unperturbed by my mind. It creates the data. And then I interpret data. You interpret data. Our neural networks are a little different. We anchor to different mode of thinking paradigms and interpret differently, which is natural. But human observer does not influence the observation.
So what I would like to take, my take from your presentation, or rather your idea about CTF, complex tension field, is that maybe it's a better way of thinking about the speed of light. It's a better way of like deriving it instead of just thinking it as something God-given.
Yes, because C is a secondary parameter. Primary is the tension properties. In fact, that's why I derived this silly undergraduate way.
And I think if you talk with John Macken about his theory, which has another explanation about why you have a tension field, and in his model you have also 0-point oscillations of the possible vibrations you can have in a gravity system, or rather in a space that vibrates. In his model, he has a possibility to probably derive the speed of the sound velocity, kind of, in that medium.
Yes.
And that could probably depend on the size of the universe in his model. He started with a very small room space, and then thought about what happens when you have just one single mode of vibration there, and then when you expand it, what happens? Then it expands very fast because you have 3 dimensions. And then after just a very brief time, if you imagine you do have a speed of light that is the speed of gravity waves. If you have the speed of gravity waves inside there, within very short time, you have so many possible vibration modes that it behaves like a very hard rigid. And then everything that happens inside that very hard rigid appears like quasi-particles in a solid.
Okay.
So it's like a sea of water, but very, very rigid in his idea.
Yeah, in fact, my belief is that the space, whether CTF concept emerges as the right way or not, but it is obviously from light propagation, extremely energetic, high stress medium. And I don't think it is built out of particle. The quantumness comes.
But John Macken and John Williamson have talked about this and agree that there is an extremely very small ripple on top of very, very, very stiff, hard tension.
Yes.
That could explain the quasi-particles that we are, right? very, very minor. You wouldn't notice it if you weren't actually one of them.
Yes.
You see?
An assembly of them.
But he can see that there has to be a maximum density of those excitations, and that's the black hole, the maximum density of a black hole.
Yeah. Now you're.
And that probably is observable. So that's
Yeah.
actually an experiment that can be done. What is the density of the black hole in the center of every galaxy?
Well, there are so many assumptions behind those measurements that I would not really hang my entire, my life on that.
Yeah, no, so I'm saying you can't observe it except by looking at the black hole, because that would be the only observable effect. And it's difficult to measure the density of the black hole.
Yeah, in fact, I understand the black hole as something physical is real. Whether it is the current black hole theory or not, that's what I have some doubt. But I could imagine this way, that since the entire galaxy is moving, okay, and creating gradients, so all the stars are creating.
What do you mean with gradients? Now we have to be you have to use the nomenclature that we understand.
Okay, I define the gradient this way. I'm picking up from general relativity's Einstein's concept that gravity is a curvature in space. So I should use the probably word curvature, but I call it potential because
curvature would be better for us.
Yeah, okay. So it's the curvature, but to me it's the potential, because even in classical mechanics we use the word potential, and even,
yeah, but then that potential in my word would be the gravitation field.
Yes, to me it is not a field, it is a curvature of CTF in CTF. So
and the highest tension field, that the highest gravitation field we've observed has been that experiment that where you only saw a tiny fraction of proton radius on a scale of kilometers.
Mm-hmm.
When two black holes collided and merged together, and that's the experiment that was seen. You know, the gravitation experiment, where you observe the whip two holes going together.
Yes. Yes.
So it's so small. You have, that's the only experiment where you actually see the effect of it, where you actually see the absolute tension.
Okay, I mean, this is obviously, frankly speaking, beyond my able to comment in a scientific way, because I have not spent enough time there. I'm just.
But it would be good if you use curvature for the when you go back to your galaxies and the curvature.
Yes. Okay.
I think potential is also a thing that you can use here as well. Gravitational potential, curvature related to one another. So it's not that one is exclusive over the other. So, but I think
gravitation is a secondary effect of the. I mean, and the tension in the field is the primary effect.
I agree with that. But
he's
I'd like
about.
to come back to this. I'd like to come back to this, talking about the complex tension field, Chandra, and asking you. We're talking about complex tension field as in a two-component tension. Do you mean complex in the sense of two components here, in sense of real and imaginary, or do you mean in terms of epsilon and mu?
Okay, that's right. I do not at all mean complex I is involved. In fact, I do not like the complex math I. In quantum book, I have written that it is a fortunate coincidence. It's really square modulus gives you time average, which is built into our measurement. So I does not represent anything physically real. But when you do square modulus, it gives you time averaging if you don't use cosine omega t or cosine 2 pi nu t. I use the word complex in the sense that we only now know for sure two physical properties, epsilon naught, mu naught, very well established many different ways. there has to be many other properties that we do not know. And that's why I'm saying, in that sense, it is complex. We do not know enough.
Okay. It's complex in the sense that it's two components, and perhaps there are other things like a torsion or compression, or so forth.
Yeah,
Yes.
I think it's good to have complex because your theory adds complexity.
That's true.
We can't observe it, but it's another way of thinking what we are.
No, I think eventually we should be able to validate that. Even though we are built out of it, we are assembly of oscillations of it. But the fact that the creator has created DNA molecules in such a way that it can start analyzing itself. We psychologically self-analyze, so we should also be able to self-analyze nature itself. And we are heading that way anyway. So
but I see that as a wish from you. I don't know if it's real until you've proven it, right?
Of course.
You're trying to be the...
Yes.
Chandra,
Chari.
Chari?
yeah, I really enjoyed your talk. I should say that first of all, it has been a long time since we met and talked, but then I think this is a wonderful talk that you gave today, and I really appreciate that. I got a question though. I got a few questions indeed. In fact, lots of thoughts were crossing my mind as I was listening to you. My first question was, maybe I made to you some time ago. When you talk about a complex tension field, is it not another effective field theory? In what sense it is different from current mathematical approaches that people are doing?
Is
it simply the terminology difference, or is it something totally different in terms of what people are trying to accomplish? That was my question to you some time ago.
It's not totally different. It is field theory. In fact, in a way, I see that Einstein dream can be much more implemented here, but
that's right.
I believe you'll have to dunk special relativity. Okay? But otherwise, yes, it is a field out of which both the observable particles and waves are emerging. So it is the old field theory in fundamental concept. Yes.
Indeed, I should not brag about what I'm doing. The very first time I gave a talk in Spain was about there are no point particles, definitely no waves in the particle physics.
That's
and
true.
Then 4D spacetime was one of my first attacks which I was doing. But I got an experiment also I want to suggest to you, but I will do it later on, okay? Because this is not a forum where I can just take up all the time of yours with respect to other people.
Call me or write email and then.
But I'll give you a call or send you an email, because I've been thinking about an experiment about the interference of the optics. In fact, you're an expert of that. And then I think, and again, I sent a note. Is it the Zeilinger's experiment which you're referring to when you talked about the neutron diffraction?
Zeilinger, yes, Anton Zeilinger. Thank you.
Anton Zeilinger, 1988.
Yes, Anton Zeilinger. He's a brilliant experimenter.
Yeah, that's the one.
I mean, I trust his experiments, even though I do not agree with most of his interpretations, but I trust his experiments.
Yeah. Zeilinger from Vienna has done lots of experiments in optical interference as well as the neutron interference also. But he's mostly in the optical side, in the quantum optics, as well as the CHSH formalisms.
Yes.
So that's what I thought you were referring to. I was just trying to clarify that.
Thank you for reminding me.
I will communicate with you because there's a lot to talk about it.
Okay, good. Thank you. Okay, who's next?
I'm sorry that Viv wasn't here for that. I think he will enjoy, Viv Robinson, I think he would enjoy this talk very much.
Yes, because I liked his chemistry approach towards particles, etc. That's beautiful.
Well, Viv actually, the beginning of his model,
he reminded me of Linus Pauling. Okay.
Viv, he builds not only, he starts out with epsilon naught and mu naught as his foundation. And he derives the structure of photons from that. He derives the structure of particles from that. He builds the entire universe.
So we have
epsilon naught and mu naught. It's beautiful.
We have a lot of commonality, at least in the foundation. And I liked it because Linus Pauling, actually quantum mechanics was fishy in the early days until Linus Pauling brought in his chemistry and wrote the book and showed that how very nicely it is helping people. And even now, those who are doing molecular quantum mechanics, they're really in a way doing chemistry. But the molecular association, dissociation, that's where quantum mechanics is so beautifully successful, and the physicists have gone into that field. In fact, the physics American Association of Physics, they have a dumb-up group, Atom Molecular Physics. Very, very good group. Okay, who's next?
Any other questions for Chandra then? Well,
I'm thinking about the helium-4 superfluidity thing again. I think it can be proven by mathematics easily by just looking at two moving smoke rings with different velocities, that they wouldn't be able to observe the effect of the drag if you use the frame of one of the smoke rings to measure the other.
Yes.
You wouldn't even need to do the experiment.
And I like the smoke ring concept. I think electrons are more like small smoke ring structure.
Yes, I'd like to learn more about electrons by doing smoke rings. Actually, I think it's I think it's more like the neutrino, the smoke ring.
To me, neutrino would be fundamentally different from electron in structure. Again, my intuitive, I'm not a particle physicist, so you may ignore it. Neutrino maybe it's more like a hump in the CTF, very low energy hump. It does not have much structure.
You know, neutrinos, they can sit on top of each other and they don't interact. Electrons, they wouldn't be able to sit on top of each other. I think these smoke rings would actually pass through each other without any effects. So they are more like bosons.
Yes.
Chandra, you mentioned about particle, which were you referring to muons time dilation?
Okay, give me a
moment. Were you talking about the muons time dilation? The lifetime of a particle increasing in the cosmic rays as they come down.
I was throwing a possible because a lot of time people have, because I was saying that SR may not be really a very useful theory. It's more a bottleneck for us to proceed to. But if I hear that, then a lot of people said the muon's lifetime increases, and that is given by special relativity. There, my point is, it is a partially stable, so inherently it is already unstable because the full resonance did not come in its structure. So, but as it gets the kinetic velocity,
I'll tell you a funny thing about it. Let me tell you.
Becoming stable out of velocity.
No, I use this a lot. Okay, just a minute. Let me complete this. I use this a lot in our own experiments when we do the pion lifetime measurements and pion cross sections. When we do this in the laboratory, we do that. Funny thing that happens here is the following. It is not a time dilation, length contraction, but it's a length dilation, time dilation, in fact. So if you are in the muons frame of reference, and if you look at my laboratory, you would see the lifetime is only 602 microseconds, and the effective distance is only 600 meters, in fact. Whereas I see them coming from kilometers, and I see them coming from seconds or even longer than seconds, in fact. So what I'm saying is, what I observe in the laboratory is not length contraction, time dilation, but I'm observing length dilation as well as the time dilation. Nobody mentions this. Nobody talks about it because all we are using is time dilation to make my measurement, in fact.
No.
This is so funny.
Chadi, let me rephrase, not time dilation, rather lifetime increased.
Yeah, that's right. But that's we expect. Yeah, but we explain that in terms of time dilation when we explain to our undergraduate students.
That is, in my viewpoint, that is a wrong approach.
It's wrong. It's absolutely wrong. But we do this all the time. When we ask a question, what what's happening, the length, in fact. The length is also increasing, time is also increasing.
Thank you. You're supporting my postulate based on experiment. Thank
Yeah,
you.
we do this all the time. It's so funny.
We should write some notes somewhere jointly.
We did. In fact, in my book, it's written there.
Oh, okay. You have written already. Okay.
Yeah,
right.
when I wrote this book in the last year, which was published, we did address this question also. And indeed, we do bring out how the four-dimensional space-time is not only physically wrong, it's also mathematically inconsistent. It doesn't have a mathematical rigor. In the sense, C is a parameter which depends upon all the four coordinates. And you lost the linear independence of the parameters when you do that. Yeah. And I cannot understand how mathematics could be so screwed up for the last 100 years.
Yes, in fact, that's why I politely said that SR is actually bottlenecking our progress in physics.
Yeah, I think you're right.
I mean, literally, once the physics community globally accepts that dunk SR, the physics will start booming within a decade.
And the people forget, they become dogmatic.
Yeah,
that's what happens.
Heaven forbid that we become
dogmatic. That's also an enormous waste of energy. All the energies, dark matter, dark energy are actually held by CTF, and that's what gives the universal stability with 4, 5, or 6% as manifest energy.
Yeah, I'd like to say that in CTF and in John Macken and my word, the dark energy is very much easier to understand. It's just that's the basic everything runs on top of, and you don't see it because you don't interact with it because you're not dark energy yourself. It's just it's like the experiment with the observation of the collapse of two black holes. We don't observe it. They made an experiment where they could actually see an effect of it, but we normally don't observe it. That effect is so small on our scale that we don't see it normally. So it's a fantastic experiment that they managed to do it.
Actually, I have started thinking a little bit, but not yet. So I'm not going into further detail. The black hole, to me, is not as it is being described. But obviously, there is something serious congealed, and I'm still nurturing in my mind how to model it from purely CTF standpoint and various gradients in CTF, because CTF itself is stationary. The gradients are the producing the so-called force, meaning that those the little loops or matter assembly can follow those gradients. But CTF itself remains stationary. It's like I create a vortex in water and move my hand, so the vortex is moving, but the bulk water is not moving. But I'm further conjecturing that what looks like physical vortex in real water, okay, that's actually those turning, churning are also gradients, but the field itself is absolutely quiet, like in nirvana.
Would that be observable, or what do you think?
Only indirectly. Only you'll have to figure out, because something not moving at all, and we are.
Let's assume now that, or I assume now that you won't be able to see the drag effect that you wanted to see. So that's the experiment that would prove that you had the CTF. Yes. Now, let's assume you can't do that, but assume would you be able to see another effect of it by looking at the gravitation experiment from another viewpoint, where you actually see an effect, although it's very, very small when two black holes collide?
That's where I am confusing myself a little bit. Right now, if I say CTF is motionless, stationary, okay, then I have to interpret everything else, which are force and other things, as gradient property built into it. Like, for example, this when I'm forcing a spring up on electric vector, okay, is really some intrinsic property has changed in that physical location, which as it is increasing in behavior, it is trying to create what we call magnetic field and other kinds of curvature. And if the electric vector collapses, everything goes back. In fact, that's how the electromagnetic wave is propagating, that nothing physically moved, but these gradients created in it dynamically keeps on moving because the CTF is trying to get rid of this perturbing energy. So from that model,
I see it as you can have swirls, you can have rotations, and
yeah.
if you have a rotation, you have to have it closed, otherwise it wouldn't be possible to create it, you know. And
Yes.
you have, and if you have a swirl, you have to have an anti-swirl. You see?
Yeah, well,
Because everything has to be null on average.
yes, that's the other point. That is, how did the particle get created first? Okay, that's a fundamental.
But if you cannot, if you look at the experiment with helium-4, you can't create one. You have to create two. You can't even create just one.
Energy conservation, yes, but that's where more thinking is needed, and that's why maybe the centers of the galaxies could have some.
So usually you have something you stick into the fluid and start the whirl, and then the other whirl gets hold on the stick.
That's right. You have principles other than energy conservation here. It's angular momentum that you've got to swirls. Yes. You have a swirl and anti-swirl.
Yes, I understand. But again, they're indirectly connected to the energy also, because momentum mv also implies half mv squared in some other sense. And, or maybe we need to really define that momentum itself is something totally different from energy. I never thought of it.
Remember that the total energy is given by both the angular momentum and h nu as well. So each one accounts for all of the energy, but they're related through a linear equation. So, so it's just double counting if you try and do it twice, but they each represent the total energy.
Okay. Yeah, in fact, at some point I said that the only way we can develop unified field theory is that we take the working theories, we take the list of fundamental postulates behind each of the theories, and then try to integrate them into one integrated set of basic postulates. Then try to build. I don't think we'll have one equation giving everything. Universe is too complex. But we should be able to have unified set of postulate out of which we can build different working theories and keep advancing. As our knowledge advances more, we should be able to pull out more postulates and see how we can integrate that with the original set, meaning that Newton's postulate, Einstein's postulate, and quantum postulates, they all have to be iterated as we advance.
All of these are providing constraints on what is and isn't allowed.
Yes, yes. And the constraints will come from trying to integrate, because obviously we know from Newton's integration, the gravity, Newton's gravity, Maxwell's integration, then we are trying more integration now in the modern, starting from 1905 forward. So integration concept is an extremely important, powerful approach towards physics for sure. But we cannot assume that the foundation of physics has already been built. That's a very wrong notion.
Physics is by no means over.
We'll have to rebuild over and over and over and over. That's my key point.
Yeah, back to basics. That's what we are doing.
Yes, yes. That's why I like your approach.
Okay. Any more questions from another angle from anyone at the moment on Chandra's talk? Anyone else like to chip in on relativity or frame dragging or whatever? Any more questions? Good.
I think I didn't stress enough that I think about it as quasi-particles on top of the tension field. And so, John, you and I, John, yeah, there is no other John here. You and I, we are used to talking about solid state and the quasi-particles of electrons and phonons in solid states. Yeah, so there is a nomenclature there if you read solid state physics and crystallography that maybe we can use better to talk about the complex tension field.
I think what Chandra's talking about here, the complex tension field, the nature of space and time, the underlying medium, whatever it is, whether it's a stadium in which we operate, or whether it's an illusion which is caused by the fact of the mathematics of reality, as it were, is an open question. It's one of the things we're investigating at the moment. It's very difficult to get into, as you've stressed yourself, Joachim, because we are part of that thing. So if that thing is a stadium in which we sit, is a kind of framework in which we're trapped, or which is a feature of the nature of the way that interactions take place, is an open question, and perhaps one which will never be resolved in the sense that it can't be looked at. But that's part of what Quicycle is all about, of course. So hopefully we'll get as far as can be got in the process which we're all following with this.
Well,
yeah. So the question for me that can be answered by going deeper into this complex tension field and perhaps John Macken's theory is, what is speed of light? Where does it come from? That's the question I would like to have answered by this. It doesn't actually, you probably can't derive it because you can't observe it like God, because you're inside it, you see. But it would be nice to be able to understand it better.
But given epsilon and mu, you've got it.
Since you brought out the God, I'll say this, that we are conscious, we are trying to understand this creation, but our consciousness is emerging out of a bunch of neural net which are built out of atoms, built out of electron, proton, neutron. So in a way, the creator has given us a biological structure.
Now that the creator is evolution, you can't talk about another creator in this group, I think.
Yeah, no creators allowed. Let's stick with the physics. Sorry.
No problem.
Another forum for that. Any more questions on the physics? Gentlemen, it's been a wonderful session again. Chandra, thank you for a wonderful talk. That was very stimulating, great fun.
Staying together and asking questions. Thank you very, very much.